With us now, we have Larry Holder, who's a professor of the electrical engineering, computer science department, a computer scientist himself. He can tell us more about himself. Um, he and his wife are friends of ours. We've actually stayed at their lake cabin, so we appreciate that, Larry. That was a real special time for us. But he's going to talk about graph mining for insider threat detection, and he's going to finish out the day. So, Larry, you want to go ahead and take? I guess you got your screen shared and see you up there in the corner. So go ahead and take over.
Okay. Well, thank you very much. As Bernie mentioned, I'm a professor in the electrical engineering computer science department here at Washington State University. And I've been doing research in AI machine learning for a while. 30 plus years now. And a lot of my work has been focused on graphs and networks. And in particular, we've looked at methods for finding anomalies in graphs and networks. And a lot of times those anomalies are representative of an insider threat if the network or the graph is used to represent the behavior of people in an organization and so forth. So this presentation will be kind of interactive. I'm going to run some algorithms and show you the results, and you can actually download the code and data and follow along if you want. So if you go to this website down at the bottom here, you'll see links to everything. Let me see if I can switch here. So here's the website. If you go there, the slides I'm presenting are there. The exercises I'm going to go through are there. And in particular, you'll see a link to our graph mining code called subdo. That's c-subdo.zip link. You can get that. And then our graph-based anomaly detection code, GBAD, you can get that as well. And I'll mention some, and I should mention one of the data sets we have is this ID process 2.g. If you want to grab that, we'll be playing with that as well. So anyway, I'll refer back to these as we get closer to using them in the talk, but you can go ahead and download them if you want. All right, back to the slides. Okay, so what I'm going to talk about today is first just a really brief description of the insider threat problem and the typical approaches that have been taken. And then we'll get into a description of graph mining, which is the approach we use to look for these threats. And in particular, we're going to look at two techniques. One is pattern learning in graphs, where we're looking for common patterns. And then anomaly detection is where we're looking for instances of these patterns that are different in interesting ways. And so it's kind of a two-step process. First, you learn what the normative patterns are that's going on in your network, and then you look for subtle changes to those patterns. And then, of course, we'll look at how we can use this to detect insider threats. And I don't know if I can see electronic hand raises, but feel free to interrupt me at any time if you have questions. So the insider threat problem, I'm sure you're all aware of data breaches that have taken place over the last several years. This graphic at the top right kind of goes in reverse chronological order, and it's showing that the number of compromises and the number of victims is going up pretty steadily. Had a particularly high numbers early on, those are getting better. Fewer victims, but still the number of compromises is increasing. And so, a compromise or an insider threat in general can take on a lot of different ways that can happen. And so one way is that it could be an authorized user within an organization who is just not following the security policies, either don't know them, don't want to use them. But there are also those that have malicious intent where they're trying to, steal data, destroy or break systems. But most of the time, the malicious exploits are involved in, taking something from inside the organization and bringing it outside the organization. And so, that can happen at a lot of different levels, in terms of, like email, web browsing, file editing levels. It can happen at lower communication levels. And so there's a lot of places to look to try to find evidence for insider threats, whether it's, again, the kind of high level commands that are going on a workstation or, down to the packet level in terms of low level communications. But the reality is that most, or well, in this case, 35% as data from 2 years ago, a lot of the security breaches that happen are due to insiders. And again, that can be malicious or not. It could be social engineering from somebody outside the organization, impacting somebody on the inside. So obviously we would like to use our tools, AI and machine learning, to try to detect these insider threats. And there's kind of two pieces of that. One is, kind of a forensic piece where, something has happened and you want to go back and see, you can go back and look at the data and see what happened. But obviously we would like to predict these threats in advance. And so that's a lot harder problem and, is fraught with lots of issues, even in terms of privacy and so forth. And of course, false positives. You don't want to accuse someone of being an insider threat in the future and being wrong. So it's a big problem. I didn't show anything about, the costs involved, but they're in the billions of dollars of, what it costs to protect systems and to clean them up after an incident. So how do we typically try to detect insider threats using, computational means? And one of the most common ways, and this is kind of the way that viruses are detected, is to just monitor usually external interactions. So this is communications going in and out of your organization. And there's lots of virus patterns and rules that can be applied to things. But of course, the 0-day attack of a virus you've never seen before is almost impossible to detect. However, if you have someone in your organization who is planning something to exfiltrate information or allow some external entity access on the inside, there's usually some preparation and even some behavioral changes that go on. So that's why, the next step would be to try to build behavioral profiles of either individuals or typical employees in a particular position. And, once you build those profiles, then you can use them to monitor behavior and detect when the behavior changes. If you want to do it this way, where you basically want to come up with patterns and rules for an insider, you need training data. And so that would mean not only data for normal behavior, but data for the illicit behavior. And I don't know of any company that wants to share their data on illicit behavior, let alone data on behavior of normal employees. So all of this would have to go on internally. And then, of course, you don't have a lot of examples of, insider threats. You're trying to have zero of them, in fact. So there's usually limited data that you can use to train a system to either learn a pattern of an insider threat or learn to distinguish insider from normal behavior. And so, another approach would be to just kind of take a pure statistical approach where you're looking at certain features of a person's behavior or properties of a machine or some system in your organization. But the one thing that these statistical approaches usually do is they watch a bunch of different sensors or features, but they don't look at the relationships between them. So you might see a major increase in traffic to a certain system that somebody's trying to break into, but you wouldn't perhaps notice that a person is making just slightly higher traffic to a set of machines that are interrelated. And so that's really where graphs and networks come in, is that they're very good at modeling or representing relationships. And in our work, we think that these relationships are an important feature to be able to predict insider threats by looking at normal relationships and then looking at new relationships that may be anomalous given the people involved. So here's an example of some work we did on insider threat detection in a government ID processing facility. I think it was a passport facility in Hong Kong. But the general, the general process is represented on the left, where you have someone applying for, say, a visa. They interact with the frontline staff. The frontline staff kind of creates a case, and then you have case officers and approval officer. Approval officer will assign the case to a case officer. The case officer will investigate, perhaps discuss it with other case officers, and eventually make a recommendation back to the approval officer, who then relays it back to the frontline staff and or the applicant. And of course, throughout this process, a lot of accesses are made to various databases. And so in this case, all of that interaction was monitored. And there were several anomalies that popped out from the data. One on the top here is a case where the frontline staff is reviewing a case in the database, and this is basically not allowed. And this basically came about when some celebrity is applying for a visa or some change to their passport that would indicate where they've been or where they're going. The frontline staff can leak that information to, say, the media, because they know where someone famous is going. And so that was an obvious anomaly in this case when you compare what actually happened to what should be happening, which is the process on the left. Another type of anomaly we found was a case where a case officer who wasn't assigned the case made a recommendation on the case. And so, the part of this graph that's in black and gray, we see the approval officer assigning the case to a case officer, but that's not the case officer that makes a recommendation. So again, this was an anomaly that our system picked up. And so that's the kind of anomalies we're looking for. In other words, we have the context of what we call a normative pattern. So that's kind of the thing on the left here. And then we look for slight deviations to that pattern. And that's really what distinguishes our approach from a lot of others. A lot of other approaches would just look for noise and outliers. So they might say, well, if we see a lot more review case links than we've normally seen, that's unusual. maybe it is unusual, maybe it's not. It kind of depends on the context. If we have a lot more, applications, a lot more case officers involved, and we might see a perfectly normal increase in review cases. So in our case, the idea is that this review case is unusual given the context of where it's happening, which is, this is the context of a single event of an approval going on, and then we have this unusual review case edge in here. So that's kind of where we're headed in terms of trying to provide this technique of representing data as a graph, so we can explicitly represent relationships, and then looking for anomalies in the patterns that we find in that graph. And those, maybe they're insider threats, maybe they're not, but they are usually worth further investigation. All right, so all of this falls under the general kind of AI term of graph mining. So I'm going to talk a little bit about graph mining, and then we'll talk about our first step, which is pattern mining, which is to find those normative patterns. And then we'll talk about anomaly detection in graphs as well. So a little bit of overview on graph mining first. So a lot of things, almost anything, can be represented as a graph. And so here's some examples of phenomena that have been represented in graphs, and specifically for the use of analyzing those graphs and extracting information or knowledge about the behavior that's going on. So in biology, we can look at the interaction between proteins, and that tells us something about what a gene would, what function it has. In social networks, say like Facebook, we can look at the interaction of people within the network, and we can ask questions like, what type of person would buy my product? So I can look at all the people that buy my product and try to find patterns, and then look for the instances of that pattern elsewhere in the network for people that match the pattern but haven't bought my product, and those would be ones that I'd want to market it to. The internet itself is of course a network. At its simplest, it's nodes and links, and again, we can look for patterns of behavior. This is one of the first places we would look to try to find evidence of insider threats or just attacks on different systems. The World Wide Web, with its web pages and hyperlinks in between, can be represented as a graph. And we can ask lots of interesting questions about that. A common question is, can we predict, for a certain web page, can we predict whether someone's going to click on a link or not? And, again, we can look at other people's patterns of behavior as they move around the web. And based on those patterns, we can predict other people's behavior. And even the power grid, which a lot of work goes on at WSU on the power grid, that can be represented as a network of stations and lines at a very abstract level, and that can be used to look for patterns of behavior, say that could help us prevent brownouts or blackouts. It can also be used to look for anomalous behavior that may indicate an attack of some sort on the power grid. So those are just a few examples of graphs that are used to represent very large groups of entities, and allows us to ask questions about their behavior. One of the biggest problems with dealing with graphs is that they're big, and they're getting bigger, and they are changing constantly. So, a few statistics. So the World Wide Web, I was looking up these stats yesterday, and they're still pretty accurate. There's about 2 billion websites, give or take. There's a lot of dynamic content out there. So, is that a website or not? but about 2 billion that you can visit. And then the hyperlinks in between them, the edges in our graph, about 1 trillion, and about 250,000 new websites pop up each day. So if we want to analyze a graph like that, I mean, that won't even fit into most computers, let alone the fact that it's changing so rapidly. If we wanted to look for patterns yesterday, they may be obsolete today. So very challenging to analyze graphs. Facebook, a social network, has about almost 3 billion active users. And, there's a lot of content that's being posted, by some estimates, 30 billion pieces per month. And people are interacting with that content and with each other. And, so it's a wonderful network to analyze and ask questions about. But again, it's too big to really look at as a whole. Another example of a social network is Twitter. And I have a little movie here that shows a Twitter graph kind of growing over time. And so not only does this introduce, its sheer size introduces a lot of difficulties for graph mining, but the fact that it's changing constantly. So what you're going to see here is that as these tweets start coming in, and this is a live feed essentially, when one person retweets a tweet from another person. So I see a tweet from somebody and I like it and want to retweet it. And so when I do that tells everyone that I follow the original person. So person A tweets, person B retweets it, and that means B follows A. So when we see that retweet, that allows us to put the link in from A to B, which is kind of the followed by link. So start this up. Hopefully you can see that. But the things to pick up from this is right away you can see some very popular people, you might call them influencers or so forth. So we're finding very quickly, they posted a tweet and a lot of people are retweeting it. And so we now know a lot of people are following them. And, that's clearly an anomaly, at least initially in this graph. And then as we, proceed, we see a few more a few more nodes that are getting a little denser. We zoom in on this particular one, we can look at the actual users. And so, when you look at a graph like this, you want to ask the question, so what are the patterns in this graph, and is there anything unusual going on? And of course, at this high level, it's kind of hard to detect unusual activity other than the one very dense graph. And so, one way we can do this is that as these retweets are happening and new edges are forming, we can we can kind of take a snapshot of the graph and run all of our algorithms on it. But the snapshot's going to get big really fast, and that's going to make it almost impossible to keep up, essentially. It's almost done. There we go. So another approach would be to analyze the edges as they're coming in, and kind of keep a running set of interesting patterns and anomalies. And then as those edges come in, we try to fix those up, saying do they support the patterns we've already seen? Is it a new pattern? Is it possibly an anomaly? Maybe it was an anomaly initially, but as we see a lot more of these come in, we realize it's normal behavior. So, again, dealing with the size of this graph is one dimension of the challenge. Dealing with its what usually called velocity, or the speed at which it changes, is another challenge. But if we look at this graph, to the next slide. So if we let that go a little further, we could get a graph that looks something like this. And looking at a lot of the individual subgraphs, we see, the pattern you would probably guess is that, there's a lot of users that have several followers. So Yuppie Will over here has about 9 followers. Others have fewer. That big one, of course, had a lot more. And so that's a fairly common pattern. And then if we want to look for anomalies in that pattern, in this case, since we have a user with lots of followers as a common pattern, when we don't see that, that is unusual, and we could consider that an anomaly. And so here's a case where we have a user with 2 followers, but only one of the followers follows another user. So in this case, this middle red node has 2 followers, but only one person follows that other user. And then over here we have 3 users that are all followed by this one user, but they're not followed by anyone else. So it's pretty unusual if you have a bunch of people that are followed by a single person, but none of those people are followed by anybody else. Again, probably not an insider threat, but this just give you an example of the kinds of anomalies that we can find in data like this. So a little bit more, overview and some terminology. So you probably already get the idea behind a static versus the dynamic graph. So this graph on this slide is static. The Twitter graph we saw before was not. But for a static graph, we, of course, have our nodes and our edges or links. And then each of those nodes and edges could have different attributes on them. Here we have a color attribute on each node, but it could be, a node is a person and they get to have a name and an address and age and so forth. We don't have to represent everything as a link. And then the patterns we're going to find or we're going to look for are, just basically commonly occurring subgraphs. And typically the subgraphs we're after are connected. So it's not like we're looking for, 2 small pieces of a graph. And then anomalies, again, for us, to distinguish from the others. So as I mentioned, an outlier might be, an unexpected subset of nodes. So we might see, a pink or, a color we don't have here, an orange or something, that would be unusual. But not necessarily an anomaly. It could just be an outlier. And then noise is usually what we would consider expected deviation. So, for example, if we looked at, in this case, the probability distribution over the edge color, it'd probably be pretty evenly distributed over the 3 different colors we have here. 4 different colors. You'll say, 25% chance for each. But, we might over time see a few more red ones than the rest. And that, is still within the standard deviation of the number of red nodes we see. And so while it's a deviation, it's one we would expect. And so we don't consider that an anomaly either. And so specifically, we consider anomalies to be a deviation to a normative pattern. So once we find the pattern, we then find close matches to that pattern that deviate in a small way, but they're still grounded in the context of the overall normative pattern. Let me jump ahead here just to drive this home. So say we have, here's our graph we just saw. And if we look for patterns in that graph, we may find, here's a pattern of four nodes and four edges that occurs multiple times. Of course, within each of those is this triangle pattern. And you also notice that the patterns overlap. In a few cases, they overlap by a node. Down here, they overlap by 3 nodes and 3 edges. And so, there's some question about, so in this bottom left, is that really 2 instances of this pattern, or is it really just one pattern and we just happen to have this extra red node hanging off of it? So that's the type of normative pattern we're after. And then in terms of anomalies, so here would be an anomaly that we're after. So it's a close match to the normative pattern, but it's missing the red node. Instead, it has this blue node here. And so we would flag that as an anomaly. And again, it's anomalous because it's in the context of what usually happens. It almost matches a normal pattern, but it deviates in some way. So backing up here, so we talked about static graphs. Of course, in the dynamic graph, the graph is changing over time. And as I mentioned, there's usually 2 ways to handle this. One is to take the static snapshots over time and kind of run static algorithms on them. Or we can take more of a streaming approach where we either analyze the nodes and edges as they come in, or we sample, we kind of watch the graph for a certain amount of time and build up a time window version of the graph and just analyze that time window and then move to the next time window and so forth. But, in either case, these graphs are large and they're changing rapidly. Some sort of a sampling approach is needed. You can't just grab the whole graph and analyze it every minute or hour. So in terms of patterns, a dynamic pattern typically is a static pattern, but it also tells us how that pattern was constructed. So in what order did the nodes and edges come in? And we can learn patterns in that. And then anomalies, of course, would then be both anomalies to the static part of the pattern and anomalies to the ordering in which the pattern was constructed. We're going to mostly be talking about static graphs and static patterns and anomalies, but we'll see a little bit about dynamic ones, and we have systems that can do both. So when I say graph mining, as I mentioned, we're mostly going to be interested in doing pattern learning and anomaly detection in graphs, but graph mining encompasses a very large set of techniques, from simple techniques like shortest path to more interesting ones like link prediction and predicting dynamics of a graph, how it evolves over time. But we're going to be mostly focusing on these 2 in this talk. So again, we're after normative patterns in the graph. And the main heuristic we use for finding these patterns is essentially a compression heuristic. So the idea is that if I were to take all the instances of this pattern, the things outlined in the black dotted line, and I shrunk them down to a single node, then the graph would get smaller. And so what I'm looking for, what pattern should I, output for this graph? I could output a single green node that shows up a lot, but replacing the single green node with another node is not going to compress the graph at all. And so I'm looking for the subgraph that generally it kind of balances the issues of size and frequency. So I want one that's large and I want it to have high frequency. And if I can find such a pattern, then again, if I replace all the instances of that pattern by, say, a single node, that's going to shrink or compress the graph. And so the patterns that we go after are the patterns that maximally compress a graph. And those are what we would consider normative patterns. And generally speaking, we found that in a variety of domains, those are, the patterns of behavior that we're interested in terms of what that graph represents. And then again, once we find that pattern or those patterns, then we go and look for close matches to it. And that's where we'll look for anomalies. So a little bit more about pattern learning. So as I mentioned, we look for patterns that maximally compress a graph, and this has kind of foundations in information theory and this concept of what's called a minimum description length. And the idea is that any information can be represented, say by ones and zeros at its lowest level. And you can ask the question, well, what's the fewest ones and zeros I can use to represent something? And so in this case, if I look at this graph in the upper right, and I want to send that graph to you, as an attachment in an email message, I'm probably going to compress it in some way. And ideally, I'd like to minimally compress it. And so one way I can send you that graph is I could send you every node and every edge and the colors and so forth. Or I can notice that, hey, this graph is really composed of 4 of these little, 3-way triangle graphs. And so I could send you this description as well, saying, okay, S1 is one of these triangle graphs, and the bigger graph is made up of 4 of those S1s with some extra stuff. And, that may be a more efficient, a smaller, description way of sending you the graph than the original way. And so that's, this compression idea really comes down to if we represent the graph as, some number of bits, and we do it by, finding a common pattern and re-expressing the graph in terms of that pattern, then if we send the pattern, that's the description length of S, that's our pattern, and the description length of the graph given S, or after being compressed by S, that total amount of bits, you can say, we want to minimize that. So we choose the pattern S. We use S because it's usually called a substructure or a subgraph. But that's the pattern we're after, and in particular, we're after the one that minimizes this total description length. But it's the same as saying we want to maximize compression. And we have a couple of versions of the code to do this. If you go to our main Subdue page, you can read all about it. But on GitHub, we have a Python version, which is just called Subdue, and a C version, which is called CSubdue. And we're going to mostly play with the C version. The Python version is really targeted for streaming graphs, and the input is in a JSON format, if you know what that is. Whereas the C program takes a more readable textual input and is targeted to just static graphs. So speaking of Subdue, let's do an example here. So first of all, how do you represent a graph in Subdue? And graphs are represented by a sequence of vertices and edges. And each vertex is given a unique ID, in this case, an integer. And each vertex can have a label, which in this case is John for the first one. And then to represent an edge in the graph, we first decide, is this edge directed or undirected? So, for example, the relationship of knowing someone, John knows Jane, Jane knows John, that's kind of a reflexive relationship. There isn't really an arrow I guess it's possible that John knows Jane, but Jane doesn't know John. But in this case, this represents the fact that they both know each other. And then if we want to represent the fact that Jane works in the IT department, in that case, that is a directed relationship. So the Jane's department is IT. It's not that the IT department is Jane. And so we can specifically designate edges as being directed or not. And the edges can also have a label. And sometimes you'll see in the data that will show that you'll see E here for edges, which, makes more sense. We're calling an edge by E. And so in the subdue system, you can designate if, is an E edge directed or undirected, but by default, they're considered directed edges. And, if you want to actually use this and you have some weird labels, we'll see like some URLs a little later that have lots of weird characters in them. We can still handle that if we can, basically quote those labels. So let's see an example of this in action. If we go back to this website and I download the CSubdue package, again, this is the same one that's on GitHub. And I go into the downloads. So just, following along this. Oh, I guess you can't see that. Here's my old screen. So first we'll unpack the zip package. So if we go in there, we'll see the usual stuff, but in particular, there's some sample graphs in here. So I'll go into the graphs directory. And I think, this one is a sample graph. So we look at that. So this is, again, just a very simple toy example of trying to represent kind of a visual scene of objects that are on top of each other. So we have 10 different objects, and then we can look at their, we can describe their shape as triangle, square, circle, rectangle, again, using edges. And then we can use the edges to describe the relationship of on top among the different objects in the picture. So that's, the input. And then when we run subdue on it, let me go in here. I guess I'm using VI, old school, but instructions have you do more. But if I go into the source directory where all the code lives, I can type make to make the code. And there's several different executables here, but the main one we care about is the subdue executable. And I'm going to type make install, but all that's going to do is copy these executables over to the bin directory. And so now if I want to run subdue on that sample graph, subdue now lives in this bin directory. So I say subdue bin or bin subdue, and then the graphs directory sample.g. So I run that, and you can see it starts by outputting a lot of parameters. Obviously, we chose default values for all of these, but there's a lot of parameters you can choose, and there's a manual that comes with it that explains what all the options are. And then we see that it found 3 different substructures or patterns ordered by their compression value. So this value here is basically saying that we got 1.8 compression, which means that the compressed graph is the compressed graph is 1.8 smaller than the original graph. And that's because it found this pattern here of basically triangle on square. It found 4 instances of it. And then, when it went to compress the graph using that pattern, that resulted in maximal compression. And then it also outputs a few others. So this is a square on an object of any shape. And this third one here is a triangle on an object of, this is something on a triangle. And this one up here is something on a square. So it's some unspecified shape on top of a square or a triangle gave us the next 2 winners for compression. So that's Subdue at its simplest. Again, you represent your data using a graph, and it will find normative patterns in that graph based on this compression heuristic. Okay, I'm gonna put this over here. Okay, so Subdue also comes with the ability to visualize the graphs in a prettier way, and it takes advantage of a system called GraphViz. So if you're following along on a AWS Linux VM, you can install GraphViz using this yum command. I've already installed it, so. And the sudo here means you need to have super user privileges, which you usually do in a VM, but if you're using somebody else's Linux system, you may not. But a lot of systems come with GraphViz already installed. And there's a link on the resources page to the GraphViz website. You can download it yourself if you want. But what GraphViz does is it allows us to visualize our patterns. So in this case, say I want to visualize the entire input graph. I can use this graph to dot. Dot is the format that GraphViz uses to represent a graph. So I'll put this to, I put it here, just. So that creates this sample.dots. And if you look at that again, it's just another textual way to represent a graph. And then I can convert that to an image, but now I need a kind of a layout algorithm, an algorithm for laying out where all the nodes and edges go. And the main program called Dot is probably the best approach. If you go to the GraphViz website and look at layout engines, you'll see that there are a lot of other ones. So in addition to Dot, there's several more. I can try one of the other ones, see what it looks like. So to run it, we run Dot. We tell it what type of file we want, which will be a PNG file. We give it the sample.dot. And at this point, it would output the image just to the console. So I'm going to redirect it. That's what the greater than is. to a file. And then I will bring up a file browser. So there's our graph in a prettier layout, depending on how you consider prettier. Again, if we were to try a different layout algorithm, I think Circo tries to put everything in a circle. A little harder to see, but you can see how most of the stuff's in a circle. Got a little weird on the edges there, but so that's this dot language is kind of what Subdue uses for communicating or producing visualizations of the graphs and the patterns that it finds. And as we'll see, it also will work for anomalies as well. So if we wanted to look at the pattern that we found, we can rerun Subdue. But this time we give it this -out option, which is going to write the best substructure it found to this output file, subs.g. And we'll run it on that same graph sample. And so now we have subs.g, and it is the pattern, the triangle and square pattern. And then we can run a program called subs to dot and pass in subs g and then write it to subs dot. It wrote one substructure. If you ask Subdue to produce more than one substructure using an iterative approach, which we'll talk about later, you can get several patterns in this. But again, we can visualize it. And this subs PNG. So there's our triangle on square pattern that we found. So that's how you would visualize an individual pattern that Subdue produces. Now, another thing we can do with Subdue is do what's called supervised learning. And so what we just did is called unsupervised learning. We gave it a graph and said, find interesting patterns. But in supervised learning, we would tell it, I have a graph or some graphs of patterns that I'm interested in, but I have some other graphs that contain patterns I'm not interested in. So I don't want you to find any of those patterns. And so in this case, we want to find patterns that compress the first graph, or we call it positive graph, compress it very well, but we don't want those patterns to compress the other graph, the negative graph. And so in this example, we see that this red, green, red subgraph shows up often in the positive graph, but does not show up at all in the negative graph. Whereas, the green, green, green one also shows up a lot in the positive graph, but it also shows up a lot in the negative graph. So we wouldn't choose that. And so we're basically wanting to, compress the positive graph. So we want to minimize the numerator, but not compress the negative graph, and therefore maximize the denominator and overall minimize this ratio. Let's see, do I have that? I guess just real quick to look at a graph that has multiple graphs in it, like this one. So we have a graph. So this was work I'll talk about on the next slide, where we were looking at communication networks among different groups. Some of the groups were normal groups, some were threat groups, and we were trying to find a pattern that occurred often in the threat groups, but didn't occur often in the normal groups. So you can see we specify the positive groups, the groups we want to find patterns in, as XPs. And if we scroll down a little bit, we see XNs. So that's telling us this is a non-threat group. So we want to, again, find patterns in the threat group, but not in the non-threat group. And I think I have, you can run subdue on in the same way. So we can see the substructures. And so here's one it found. I won't bother to visualize it, but it's basically two actors communicating between each other. And this particular form of communication showed up a lot in well, actually not too well. Showed up in one positive instance and 23 in the negative graph. So this one isn't actually too good. I guess the one at the bottom here, one positive instance, 3 in the negative case, a little bit better discriminating, but that gives you an example of running subdue when you have multiple separate graphs and you want to find patterns in one and not in the other. So as I mentioned, this was some work we did in, basically trying to identify threat groups based on communication. And it was, part of a larger project that had evidence that was coming in that was collected from the field, and that would augment essentially a social network. And then, the threats that were known, or the groups that were known to be threats, were identified. The groups known to not be threats were identified, and then we could run subdue on that and try to find a pattern that we could then go look for elsewhere in the network. And if we find a match to that pattern, that may indicate that it's a threat group. And so we did this, in several different test cases, but one example of the results of getting 80 to 85% accuracy at identifying threat versus non-threat groups using this technique. Okay, and I mentioned that subdue can be run iteratively. And what happens here is that we essentially run subdue on the graph and it finds a pattern, but then it goes ahead and compresses the graph with that pattern. So in our triangle on square example, we find this triangle on square, but then we replace it with a single node or single vertex, and then that vertex is called sub1, or it has a label sub1. Then we run subdue again, and it finds another substructure, which is just an object of shape circle. And then we run it a third time, and in this case, it finds the pattern of this whole substructure on top of an object. So that would be, a triangle on a square on something. And in this case, that would be the rectangle that's in the middle of this picture. That's the only time that we have a triangle on a square on something. So to see how to do this, just following along with instructions here, we can run subdue. with this iterations argument, and we'll tell it to iterate 3 times. We'll store the results in the subs G, and we'll run it on that same sample graph. And then I will visualize the results using that subs to dot program, pass in the subs G file that subdo wrote out, convert it to dot format, and then we'll run dot on it. And convert that to a PNG image. And if we go and look at that image, you'll see it's, basically it's taking so long, but so it's basically the same image that's on the slide there. So it allows you to see all of the different substructures it finds at each level, and it also captures the relationship between, in this case, sub 3 is built from a sub 1, and it adds the on object relationship. Okay, so here's an example where we use this iterative approach to analyze 2 different terrorist networks. This is, I think on the left is Jamaat al-Fukra, and this is Al-Qaeda on the right. And we basically wanted to find patterns that occur in both of these networks, but we iterated over it multiple times. And here's kind of a blow up of the pattern that was found at the 7th iteration. Now, normally if we visualized it this way, we would see, sub 1 connected to sub 2 and a sub 3 and so forth. So we kind of, reversed that process to get the full pattern back out. And, it's not particularly, like smoking gun pattern, other than, we see that there are, multiple males involved, and that they have somewhat of a distributed affiliation to the organization with sub-organizations. So, it's only based on 2 networks, but, if we had more networks we could analyze and we found such a pattern, then, that might be a pattern that's indicative of a terrorist organization. Of course, it might be indicative of any organization. And so at that point, we would want to throw in some non-terrorist networks and run subdue in that, supervised mode, so we can find a pattern that can distinguish the terrorist networks from the non-terrorist networks. Okay, so let's see, we're about an hour in. Maybe I'll take a short break here. We're about halfway through, so see, maybe I'll start back up at 4:10 in about 4 minutes. But if anybody has any questions at this point, I'd be happy to entertain those.
Hi, Larry. I had to be online following this, so I think it's a good time to take a break, and I think 10 minutes would be fine. I don't have a question, but I just wanted to let you know about the audience a little bit. So there is a good mix of computer science students with different kinds of backgrounds. And there are colleagues from AFRL and the Griffith Institute in attendance in the room. And I know there is a huge interest in graphs. And so the topic you've heard is one of my favorites, both in teaching and research. And Larry does a wonderful job combining them with AI and machine learning, which were the topics that were dominant yesterday. So this is a treat this afternoon. So take your time, 10 minutes, Larry, and it would be nice to get back then, is all I wanted to say.
Okay. Sounds good.
No,
I know. Yeah, and that was so. Yeah. Yeah. Scroll on our chat and we'll see it. Say that, like, he wasn't there to get back. But this information. Yeah. Fair enough. Yeah.
All right. We ready to get going again?
I think this is a good time to get going again.
Okay. All right. Well, so the first half we just spent looking at, graph mining in general and pattern learning in particular, and the subdue system we have that finds patterns in graphs. But insider threats are usually something unusual that happens in an organization, and so we would like to be able to detect anomalies in these graphs as well as normative patterns. So, second half will be focused on that. So, how do we do anomaly detection in graphs? As I mentioned before, we start out by essentially using subdue to find the normative pattern. And then we look in the graph for close matches to that pattern. So, for example, here's a pattern that, or a subgraph that almost matches, but it's missing an edge. And so that would be considered what we would consider an anomaly. In other words, an unexpected deviation, but in the context of the normative pattern. And so, so the main questions you want to ask is, how big of a deviation do you allow? Because it could be completely different. And how unexpected does that deviation have to be? And generally, the algorithm leaves those parameters to the user to decide. But when we run the algorithm, we're actually only going to pass it the T1 parameter. So we're basically saying that a deviation, we consider it a deviation if the distance between the pattern S and this potential anomaly S prime, if it's a small enough distance, they're not identical, but they're close. And so we usually have some sort of a distance metric. We use what's called a graph edit distance, and we supply a parameter that edit distance ranges from 0 to 1, and we provide a parameter that means that any deviation we find has to be within that threshold of distance from the original pattern. And then the second parameter is how unexpected is this. And so basically what we do is we go and look for this deviation elsewhere in the graph. So if we went back in this graph and we found that there's a whole bunch of these near misses, these circular patterns missing this one edge, then the probability of that showing up is very high, and therefore it's not an anomaly. It's probably noise. So we can put a threshold on that as well as to just how rare does this event need to be considered an anomaly. But generally, when you run the algorithm, you only supply the first parameter, and the second parameter is used as a ranking. So we would find the rarest anomaly first, the second rarest, and so forth. And again, this you can go to this. The software is called GBAD for graph-based anomaly detection, and it's mostly developed by my colleague Bill Eberly at Tennessee Tech. And so you can go to his website to get the code. But I also put it on our. Let's see, where did it go? I also put it on the resources here in gbad.zip, and I'll go ahead and download that for later. So using GBAD is very similar to how we use Subdue. Again, you specify vertices and edges the same way, or for whatever reason, the GBAD code requires you to put quotes around all of the labels, whether they have special characters or not. We've seen these XPs before. Those were like our positive examples. And so that's how you can specify multiple graphs to GBAD as well. And if you do that, you have to give them numbers. And this is really so that when GBAD finds an anomaly, it can report back which graph it was in. Was it in graph 1, graph 2? And that's really just for us users to be able to track down where that anomaly is in the graph and further investigate. So, again, very similar to what we did with Subdue. So let's do an example with GBAD here. So we'll unpack it. And then go into this GBAD toolkit directory. And again, GBAD comes with several sample graphs, and we can look at this problem example. So that just gives you an example of how you input to GBAD. And, this is just a toy example. It's easier if we visualize it. So like subdue, we'll go into the source directory. GBAD uses that minimum description length heuristic, just like subdue. So that's why it's called GBAD MDL. And we'll make the source code and then copy it over to the bin directory. And then we can run GBAD. And the all parameter, that's basically the T1 that we have to provide. So by giving it a value of 0.5, I'm saying that essentially the anomalies that we consider can't be more than about 50% different than the original normative pattern that we found. So we'll run it on this same example. Right. And I'll go ahead and copy the output to a file. There's a lot of output. So if I look at that output file, and we see a lot of the parameters available, and we see that GBAD starts out by essentially running subdue and finds this normative pattern, which is these 4 vertices in a kind of a 3 people follows another person Twitter kind of graph. I don't have a picture of that. And then when we come down, so once we found this normative pattern, then we look for anomalies to it. And so we find this one anomalous instance that's in example number 6. And we see 2 anomalies that it points out. One is that it has an unusual vertex with an unusual label, and it has an anomalous edge, which is connecting to that vertex. So if we go back to the actual graph, and we go down to example number 6, you'll see the anomalous vertex there that it picked up on. So real simple example of GBAD. Again, GBAD can convert these graphs to the dot format and then to images. We'll do that to a few of them. One nice thing about GBAD is that it actually colors the anomalies in the graph, so you can very quickly spot them in the visualization. So I just showed you the output. So to visualize these anomalies, so just like with subdue, we can specify an output. Here we use the -dot option, and it outputs the dot format directly for us. And then we can use the dot program to convert that to an image. So let me take a shortcut here and reuse this. So I just add that extra option in, and then I convert it to an image. image. So there we can see the image. And again, you can see that GBAD has highlighted the example that is anomalous. And in particular, it highlights in red the anomaly itself. And so that allows you to very quickly zoom in on what the anomaly is. So that's GBAD in a nutshell. So let's look at some examples we've used GBAD for in the past. You might have remembered now many years ago, the energy company Enron and the basically the collapse of that company. And strangely, as part of the court proceedings of that collapse, the judge allowed the release of all of the emails that were sent among the Enron employees leading up to the collapse. And so you can get that data from this website. One of the things that came out in the trial and following was that there were some people who knew that things were going bad, and they were trying to alert higher ups about it. And so we wanted to see if GBAD could find that person, that whistleblower, if there was some pattern in the emails that was unusual that might help us spot that person. So we took the emails for the month of October leading up to the collapse, and we broke them down into individual days. And for each day, we would represent each employee by a node in the graph. And then if they emailed each other, we represented it by an edge in the graph. And so those are the XPs in the input file, one for each day. And so here's what one of the days looks like. And in particular, this is October 24th. And GBAD finds this anomaly of a vice president emailing an accountant. And that was an unusual thing to do. Vice presidents don't usually email low-level accountants. But it turned out in this case, the accountant in question was Wanda Curry, which turned out to be the whistleblower in the Enron case. So, obviously we, knew that beforehand, but, we tried to represent this problem in an unbiased way. And we think that it kind of validates the approach in terms of finding real world anomalies. I mean, I guess, from some people's perspective, Wanda was an insider threat because she was trying to tell people about what was going on. In other perspectives, she's the hero. So another problem that we ran this on was, so VAST is a conference on visual analytics, and each year they usually have a challenge problem. And back in 2009, they had a challenge problem where they had an insider threat, and they provided a bunch of information about basically a campus with buildings and employees that would badge in and out of buildings. And then within the buildings, there were certain classified rooms and employees would badge in out of that. They also monitored network traffic from all of the machines on the campus. And so, there was an insider who was essentially leaking information, and the challenge was to find the insider. And so we represented this information as a graph, of course, and in particular, we focused on the movements, both the movements and the network activity that went on throughout the day. And so this graph on the left is kind of a general template of how we represented movement. So we have a movement here with a start and an end location. And then within the end location, if there's any network traffic that occurred at that location, that's also represented. And then as the person moves again, we have kind of another subgraph that represents that movement and any network traffic that went on. And so here is the anomaly that GBAD found. And in this case, the anomaly is something that's missing. And so what's happening here is that this person is moving from outside a building to inside the building. And then the next movement observed is moving from inside a classified office to back into the outside of it, to the building. And so there's no record of a movement from the building into the classified room. And so what this probably means is that this person piggybacked on somebody else, and got into the room without having to badge in. And that person turned out to be the insider in this case. Now, again, the vast challenge is focused on visualization. So, we didn't have very impressive visualizations, but we were, validated that we did find the right person. Another example, getting down into more low-level internet traffic. There's a CADA organization that has tons of data on lots of different collections from the internet, from these high-level what they call autonomous systems, which are usually like internet providers, all the way down to denial of service attacks for an individual system. And so as you can see, the main, using this graph, the main normative pattern is that these different autonomous systems have a customer provider relationship with other autonomous systems. But in this case, this particular connection between these two autonomous systems was only had the provider link. There was no customer link. And so while this isn't an insider threat or any sort of an attack, it is an unusual case because you don't normally see one system providing to another, especially one that doesn't have these sibling relationships between them. So it could be an example of one system covertly using the internet access of another system. And then lastly, back to the example we showed at the beginning, again, GBAD is what we use to analyze this data. And in particular, we were, trying to model these 8 different types of anomalies. The first one we mentioned, this frontline staff reviews a case where they shouldn't be reviewing cases. The other one here, scenario 4, we have the approval officer reverses the decision of the case officer. Perfectly legitimate, but it happens very rarely. And so that was picked up as an anomaly as well. And so we basically would feed GBAD 1,000 cases, and there was usually 1 to 3 anomalies in the cases, in these 1,000 cases. And in each case, GBAD found the anomaly with no false positives. And just to show you what GBAD produces in this case, so here's let's see, I guess scenario 2 here. Frontline staff submits a case directly to a case officer, bypassing the approval officer. And so, here's the normal pattern of the frontline staff will submit the case to an approval officer, but over here, the frontline staff is assigning the case to a case officer. And so, not only should they be submitting it to the approval officer, they definitely shouldn't be assigning it to anyone. So it correctly identified this as the anomaly. And in this case, the assigned case edge is really the one that should be colored red, but it's colored gray because that edge is part of the normative pattern. So in this case, we'd have to scrutinize it a little bit more carefully to see that this edge, while it is typical, it's coming from a different node than it normally should. And so that's a trickier anomaly to pick up on. That's why it's not colored red here. So if this ID process file that you can download, you can go ahead and download it and take a look. I'm not going to run this example because it takes too long, but you can run it at home if you want. So you can see that, it's the same thing we've seen before. So we, have the XPs in here, this slash is a comment. But we have each of the XPs with numbers. These are the different cases, and they're, represented, using the graph structure that we saw. And so, there's 1,000 of these, so it's a pretty large graph. And I did run it on this AWS VM, and it took about 9 minutes to run. And visualizing the output, again, since there's 1,000 of these, it takes a pretty long time too. And so using a faster visualizer, this SFTP that also comes with GraphViz, it still took 30 seconds to run. But fortunately, I have it on the slides for you. So this is what the output of GBAD looks like, and it identifies these cases here as anomalous. There's 3 of them here. And then, this is the anomaly we saw back here, the frontline staff assigning the case directly to a case officer. And so it found 3 instances of that and marked those as anomalies. So that's kind of some general examples of how to use GBAD. The last thing I wanted to talk about is actually more recent work we've been doing. Unfortunately, I actually have a GBAD run going on while I'm talking to you, and it's still got a few hours to go. But kind of one of our main projects with CySER is to look at a simulator called Ghosts. And Ghosts is a simulator that's written by the Software Engineering Institute at CMU, and it's designed to be a very realistic simulator of individuals in a kind of a enterprise cyber environment. And so it actually represents people sending emails, browsing the web, viewing documents, and even running, commands on the terminal. And so Ghost actually takes over the machine. So it's kind of like you have this virtual human sitting at the machine doing all of this stuff. And of course, all of the events are logged, and I can show you, let's see. So here's what some of the log data looks like. And there's a lot more data that you can log, but I just showed a few of them. So it, each machine has an ID. This is the time in which the event took place, the program that generated the event. In this case, it's Outlook sending email. And then it keeps track of where did the email come from and where did it go. course, there may be multiple users that use the same machine. And as I mentioned, so it can do Microsoft Office documents, Word, Excel, PowerPoint, create and edit those. It can browse the web, and so it identifies what website was visited and so forth. And so, so basically, what we did is we set up a kind of our own little isolated network of about 10 machines, and let ghosts go to town and generate all of this data. And this is an example of, so what we're trying to do is, let me back up a second. Ghosts comes with 2 extra systems. See, I have. Now, this is the Ghosts website, and it talks about what it can do, but it mentions these 2 other systems, Animator and Spectre. And Animator, what it does is it creates very realistic profiles for people. So you can see here's a profile that it created automatically, and it does this using machine learning techniques. And then Spectre is another machine learning technique that generates insiders. So you basically give each person, you kind of define what an insider is. So in this case, it would be somebody who likes sports and collie, not sure what that is, and they visit this IP number. And so what it does is it essentially looks for people who satisfy that. And if they happen to satisfy it and you roll the dice kind of probabilistically, it'll turn that person into an insider, and then they'll start doing something different. So it's a pretty cool system for creating very realistic synthetic organizations that can generate these insiders kind of out of the blue. And of course, what we are looking at is, can we represent this data as a graph and catch the insider using our anomaly detection? Unfortunately, I'm not going to be able to show you that we caught them because it's still running, but I can give you a little bit about what we're doing. So this is kind of a very high level view of how we're representing the data. Users can send email to each other, they can browse websites, and they can edit files. And so what we're doing is we're taking basically 1 hour's worth of data and representing it as a graph. So here's an example of 1 hour's worth of data on one machine. It looks like Robin is the main user of that machine. She's sending emails to other people. She's editing some documents, and she's also visiting a few websites like CBS.com here. And so that's, one of these XPs and GBAD. That's what the graph would look like. And our goal, of course, would be to build these graphs. And we have an example right now where we have an insider who it's kind of we call it a blackmail situation, but it's basically what happens is one of these users will email somebody they never emailed before, and then that user will suddenly start visiting a website they never visited before, and the original user will start visiting that website as well. So it's kind of the idea of, Robin contacts Rick and says, "Hey, Rick, I've got some compromising pictures of you on this website. You might want to go take a look." And he goes and takes a look, and then they continue to communicate to do whatever it is they do. So very simple, contrived example. Again, unfortunately, I can't say that GBAT has found them yet, but it's a very large graph because this data is generated over, I think, 3 months, and so we have an hour's worth of data for each day over 3 months. It's a pretty big graph to analyze. But that's what we're working on now is basically evaluating this COAST simulator to see how well it can generate these insider threats, and of course how well our GBAT approach can find them. I will say that we did run subdue on the graph, and we did find a normative pattern. And so this is the best normative pattern we found, or I think there's about 100 graphs total. So that's 100 hours. And so not surprisingly, one person emailing a bunch of other people. In this case, Rex here is emailing 5 other people. So this pattern was found in, I think, all but one of the days. I think 93 out of 94 days. Again, it's a normative pattern. It's not unusual. Obviously, Rex emails these same 5 people every day, almost every day. So we're hoping that if Rex is our insider, he's going to email a 6th person that he's never emailed before. And so if we find that anomaly, then that would be a good, again, validation of the approach. Obviously, the fact that it hasn't finished yet, and it's been running pretty much all day, says that we've got some challenges in terms of scaling it up to run fast. Okay, so that's basically the talk. And just to conclude, I think we all know that breaches are going to continue, or at least people are going to continue trying to do them. And they're usually as creative as we are. We're trying to stop them. And so it's hard to stop. And so one approach to do it is to try to identify the insiders that will ultimately be responsible, either maliciously or inadvertently. And we feel that the relationships between people and systems, people on the network, that is an important piece of being able to profile and identify behavior, and specifically insider threat behavior. And so that's what we've been working on in terms of graph algorithms that can find patterns and anomalies in these relationships. And as I mentioned, one of the challenges is that the data is very high volume, meaning graphs are large, and it's high velocity, meaning it changes over time. Just in this case here, obviously as 1 hour goes by, more data has come in, we want to create a new graph and throw it in and see if anything has changed. And that, of course, the graph gets bigger and bigger, and these algorithms will take longer and longer. So that's a challenge. And another challenge is that we'd like to get data from multiple sources. I mean, here, this Ghost server is nice, or system is nice enough to give us data from all of these different modes of interaction of the person with their enterprise. But, we can envision wanting other information like, credit card data, web browsing from places outside of the organization, and so forth. Obviously, huge privacy concerns there, but if we have that data, how do we fuse it together with other data sources in such a way that, again, we can still deal with all that data, but we can potentially find patterns that involve multiple sources. So, for example, if Rex emails somebody else, and that person suddenly transfers money from their personal bank account into Rex's bank account, then that further validates that something nefarious is going on. So that's all I have. Thank you. And I'm happy to take any questions.
Questions for Larry?
Well, if you have questions later on, I guess I think I had my contact info at the beginning. So feel free to email me. And my website is basically this URL without the CySER at the end. So you can find more information about this work and lots of publications if you're interested.